Thank you very much for this very kind introduction. And yeah, as indicated, this is going to be a talk on quantum simulation, quantum computation with strings of calcium ions. I'm very happy to be here. Thank you for the invitation. It's a pleasure to be back here in Vilnius after a few years. I would like to show you a few ideas, what we did over the past decade, a little more than that, and in the end, maybe a few more recent things. But I'm trying to convey these ideas in the more general terms. I'm fully aware of the fact that most of you are not familiar with the subject. So if you really feel that I'm going above your heads, feel free to interrupt me and simply ask questions. I think we have the time for that. But let me just briefly introduce you to the menu of today's talk. What I would like to set out first, I would like to give you some information on quantum information processing as an introduction, how we do that in general. Then how we do that with trapped ions and how we use them in quantum information processing. Briefly tell you what the toolbox operations for these ions are, and then show you how the Innsbruck quantum computer works and what its quantum characteristics are these days. Then just a few examples on quantum computations and simulations. And finally, I would like to conclude with a few remarks on how we intend to scale the system up to larger quantum devices. And as you see here, my affiliation is not just the University of Innsbruck. The affiliation that I'm with is the University of Innsbruck, of course, but also the Austrian Academy of Sciences. That's the Institute for Quantum Optics and Quantum Information. But I'm also a co-founder of this company, Alpine Quantum Technologies, who now produces quantum computers. I'll come back to that in the end. So what is this all about? Why do we need quantum computers? Why do we want them? Am I still in the picture here? Probably. Okay. See, the generic answer would be there must be applications in physics and mathematics. But what are these? The entire hype that we see these days about quantum computing started around 1994 with an algorithm that was invented by Peter Shor from AT&T in 1994, in which he showed if you had a quantum computer, you could factor a number with L digits much faster than on a classical computer, where the length of the numbers plays a role. So the efforts that you need to do that on a classical computer grow exponentially with the length of that number, whereas in a quantum computer, they grow only polynomially. That has some effects on cryptography, especially RSA, DES, AES encryption that is used every day when you convey your emails or you make just a bank transfer with money. A little later, Love Grover from Lucent came up with a different algorithm where he showed when you had a quantum algorithm on a quantum computer, then a database search with n entries would work much faster. In this case, it's a polynomial speed up. It would work with the square root of a number of entries as the order of magnitude, whereas on a classical database, which is unsorted, you would have to look on the average of the whole database up. Now, then was suggested in the 80s, but nobody knew how to actually do that with a quantum machine, was the simulation of Schrödinger equations. This was pointed out by Richard Feynman in his famous lectures on doing computations. That is currently a hot topic, and I will show you a few examples in the end of my talk. There is something that's less known, but equally important. That is what they call using a quantum computer as atomic state synthesizer, for example, in spectroscopy, but also for other things. And what I mean with that is the following. You can use a quantum computer and the underlying technologies to program a device in such a way that it's most sensitive to a certain measurement that you want to perform. So you can use it as a state synthesizer to enhance measurements and to perform quantum measurements which are more sensitive or which go faster. And eventually, something that's more for the theorists, but something from fundamental point of view, we review quantum physics these days with what I call the information-guided eye. That's not to say that quantum physics is different than it was 20 or 100 years ago, but we just teach it differently. So we just take the more algebraic view in the quantum information language. We use expressions like entropy in the system, which was not so used often before in our system. So that's particularly interesting for just teaching physics and for learning quantum mechanics in the future. So there's a number of reasons. So let me just start with the basic ingredients, what we need to do to come up with a computer. You all know in the classical computer, the classical bit is a physical object in either state 0 or 1, or simply a switch in the position up or a switch in the position down. And with this, we form a quantum register. As you see here, that's a bit row, could be zeros and ones, could be 32 or 64 bits as in classical computers. In the quantum world, we take the simple generalization of zeros and ones. That is our old-fashioned two-level system, which we write down as this kind of a superposition. And of course, we picture that as an error on a Bloch sphere or a Poincaré sphere. That depends on where you come from atoms or from photons. So essentially, we point out that on the surface of this area, this is our quantum information, that is the superposition, and of course measurements will reveal these coefficients as the probabilities of the system pointing in the respective direction. And the quantum register, of course, the generalization of that, so we take L, these two level atoms, and initially we get 2 to the L quantum states. But when you write that quantum state down, then you write down a direct product of all these states in quantum mechanical notation. So you have plenty of these side by side. But you have to take into account, and this is what that the notation actually says, you have to take into account that they might be in a general superposition. And not just the individual ones, but all of them together. So that's what we call entanglement. In other words, we describe the entire quantum register at once. And that's where really quantum devices win. Because whenever you change now, say, one position here, anywhere in the register, the entire register changes. Whereas when you just change that, then nothing else changes right here, because no bit in this row would know anything about that one. Whereas here, sort of the register knows about each other because of that entanglement that's going on. And this really leads then to what we call the quantum speed up and the quantum parallelism. So when we have, say, n qubits, then the number grows with 2 to the n, but the computational space grows with the computational path. This is 2 to the n. So you see with already 64, you know the old chessboard game, you just add another right score, you double the number of right scores on each individual fields, then you get an enormous amount of pathways that can interfere to produce results. So the information of what you did is not exactly in the positions where you have just put the stones and just on the surface on the lake, but it's in the interference pattern. So if you just have another stone somewhere here, the interference pattern changes everywhere. That's the delocalized information processing that we do in such a quantum register. Okay, what do we need in order to do that? As in a classical computer, of course, we have to start with an initial state. That initial state is somewhere here, the arrow pointing up or down, but we have also to be able to place it at an arbitrary position. That's necessary. The more important thing is we need an equivalent of a gate operation, equivalent to the classical Boolean XOR operation. And here is the truth table of that XOR operation classically written, but of course in a quantum notation, meaning that whenever we have a controlling bit which is set to 0, nothing happens to the target bit, but whenever it's set to 1, the target bit is supposed to be flipped. But that has to hold, as indicated by this Brown-Ket notation, also for superpositions. And that is then called the C0 gate operation. That was not available, and this really is necessary to produce a quantum computer. The good message was that together, these two operations, once available, already provide you with a universal set of gate operations. So once you can do them, you can actually build a quantum computer. That was well known already in the mid of the 90s, but nobody knew precisely how to do that. Now, the blueprint then, in theory, looks like that. We start with the superposition right here initially, and then we have a quantum process, and we end up with the superposition. And the quantum process, according to what I just said, is broken down into a sequence of 2-qubit and single-qubit operations, that is rotations on the Bloch sphere or conditional rotations on the Bloch sphere of a target qubit. And of course, in the end, you have to make a measurement, because if you would reverse this, then of course nothing is gained, nothing is won. You just have unitary operations right here. So you have to put it forward, and then you have to make a measurement, project the system, and get one of the outcomes. So that really means, in principle, in the end, you have to measure you register in the end several times to get a statistical picture. That's the image, what you have if the interference pattern on the lake. You have to figure out what is my pattern that I have. But that means you run it maybe 10 times, 15 times, then you recognize the pattern, that's the result. So that's not a big overhead. This is what we have to do. And then, of course, over the last, say, 10, 15 years, we had quite a few technologies that have been investigated in this. And if you want to know more information, I would refer you to these roadmaps. There's this roadmaps in the United States based on some DiVincenzo criteria, which actually lay out what you need to do that. This is no longer continued. The European roadmap is still continued, and I think the last issue is already about 8 years old, but has the necessary information. Or if you want to know more information, I'll refer you to this Quantum Manifesto of the European Union, or here of the National Academy of Sciences report in 2019. So what are we going to talk about? Essentially, the systems that you have here are all systems that can be uniquely controlled and manipulated, meaning you have either ions and traps, neutral atoms and traps, or optical traps, lattices, microtraps, you name it, or a neutral atoms and cavity QED to convey the information. NMR in liquids has been used. Superconducting qubits come in various flavors, charge, flux, and phase qubits these days, solid state concepts and spin systems, quantum dots, and so forth. There's optical qubits and linear optics, quantum computation, and even more exotic ones like electrons on liquid surfaces and other things. Essentially, over the last, say, 10 years, let's say 15 years, 4 or 5 of these technologies have crystallized to be the ones that are currently being pursued. And these ones are essentially the ion traps, the neutral atoms and traps of various devices right here, superconducting qubits, also quantum dots and traps, that's what I call here, as superconducting qubits, flux qubits, and the spin qubits right here, and solid state concept, spin qubit, quantum dots, and to some extent also optical qubits, although nobody has shown how to really scale this. There is a company that actually tries to do that. But so these are currently the 5, say, platforms which are currently pursued. All others are still of some exotic or, say, more academic interest, are not currently, at least as far as I know, not pursued at large for commercial access. Not yet, at least. So let's come to the ion traps. The ion traps were the first and are still by far one of the best technologies, maybe not the best for scalability, I'll come back to that at the end, but some of the best technologies that are currently delivering some quantum results. That ion trap concept was introduced in 1995 by these 2 gentlemen, Ignacy Sirac and Peter Zoller, in this seminal paper at the PRL of 1995. Essentially what they said in that paper is we can use single ions as qubits. These ions are lined up in a trap, and I'll show you how to do that in a minute, individually addressed by laser beams, and then we just manipulate the levels in such a way that we use the common motion to create the entanglement between these ions. And that then provides the blueprint for a quantum computer. In principle, this is using such a bus, here it's the motion of the ions, is essentially the idea that is behind all other machines as well. If you just look at the David DiVincenzo proposal, Lost DiVincenzo proposal, Keynes proposal, and others, they use very similar ideas, also the newer ones. But this is the idea that was first proposed by Sirac and Zoller, and then there's other ideas by Milmer and Sørensen, and based gates for the ions. I'll come back to that. Essentially, what they pointed out in that paper is how to really make that CNOT gate with, say, ions, simply saying, okay, I have a controlling qubit, and I can realize the CNOT gate by just flipping the state of a target qubit if and only if there was a 1 in the controlling qubit. So what are these qubits? With trapped ions, of course, we try to make spectroscopically our life as easy as possible. There's nothing like a natural 2-level system if you just exclude a single electron in the world, no matter what professors like theorists tell you. A 2-level system is just a construct that experimentalists really have to produce in the lab. And what we do is we just take hydrogen-like atoms, for example, that have a lower state, which is long-lived, as for example in this calcium ion. And so these states, they live about a second, and other ions even longer. So all of these ions have long-lived states like that. And then you have here your qubit, and you have here the state which allows you to detect where the system really is. The same works, of course, with lower lighting states as well, say Zeeman structures or hyperfine structures. Here you just have to replace the laser that connects the two-level system, say for the Raman transition, but otherwise it works the same way. And all of the isotopes here listed in blue have been used for qubits and are being used in various scenarios still until today. So I will, for the rest of the talk, I will concentrate on this two-level system, essentially on calcium, but you can replace it immediately by just thinking Raman and doing the other things. We do the same thing in our lab, but let me just, for the sake of simplicity, stick to one optical qubit transition because that makes our life a little easier conceptually. Now, what are these traps? These traps that we are using are so-called linear ion traps. These are variants of what we call the Paul mass filter. The Paul mass filter was invented in the 50s as a mass spectrometer. Depending on the right voltages and frequencies that you apply, it's a radio frequency voltage, you can guide ions in a mass selective way through the system in such a way that they just end up in a isotope-selective way at the output right here. You can keep the ions in the center by just winding rings around it. This is a construction that we used initially, that was then copied later on. But then you can also replace these rings for stronger confinement with so-called segments. This is a construction of Boulder and Mainz. And we have then used this what we call a knife edge blade trap, which has even stronger confinement in such a way. And you can also combine these things, like for example here, segmented traps. And the newer traps have been developed mainly in the Boulder area, but now worldwide. I'll show you some examples a little later. They are lithographically produced chip traps that can carry ions on their surface, and they are now miniaturized for use for chip uses. So we have the traps. And I will just, for the sake of simplicity, refer to this old trap. You saw that on the initial picture, but you didn't know what it was. That's the old trap that we're still using since the year 2000, although we have many more, much more complicated and other traps in the lab. But this is a simple ion trap where you can actually see the distance between these two end caps right here is about 6 millimeters. The lateral distance is about 1 millimeter. And as a good ion trap, this is just a harmonic oscillator for ions. And a harmonic oscillator is characterized simply by the trap frequency. And that trap frequency is the frequency, of course, in the so-called z-axis. That's the axis along these end caps. And the lateral x and y axis are here. Typically, we have frequencies of, say, 1 megahertz in the longitudinal axis, here the z-axis, and about 2 megahertz in the lateral axis, x and y. Keep that in mind, that that's all that you need to know in order to know what the characteristic harmonic oscillator is. How does the ion trap quantum computer now actually work? What is the idea behind Dirac and Solar? Now, the idea behind Dirac and Solar is the following. We have now ions in the trap, L ions. We know we can use them either optical transitions or ground state Zeeman coherences. But we write now our state vector in such a way, psi is the state vector, where we just discriminate here the internal information. That's whether the system is the ground state, excited state. These are the amplitudes of the quantum mechanic notation. And we have a direct product here. This is the center of mass motion. And that center of mass motion inside the harmonic oscillator is supposed to be in the ground state. Why? Now, here's the idea. Suppose these ions are sitting there in the ground state, right here. Then they are sitting here side by side. They're completely motionless because there is no phonon in the system. How should the target ion actually know that the controlling ion has an excited state amplitude? Of course, there's no way that this system knows this. So there's no way you can do that conditional CNOT gate operation. What you do instead is the following. You just point the laser to the first ion. You say, okay, I just look whether on ion number N or I in the center right here, there is a motion. So I map the excited state amplitude from that ion to one phonon in the bus. So I just rewrite the internal excitation that I need to for the controlling ion to a one phonon in the bus. How this works, I'll show you in a minute. And then you just go to the second one and make a transition on this ion if and only if there was a phonon in the bus. And I'll show you that in a minute how to do this. Once this works, then you go back, take the one, make the reverse operation, and introduce the same thing here. So you leave the controlling qubit as it was before. You have just used the intermediate bus, the phonon, as conveying for conveying the information that there is an excited state amplitude. So in other words, if you want to achieve that, you have to be able to individually address the ions, efficiently make single qubit operations. You need a small decoherence of the internal and the emotional states. And of course, your quantum computer is then realized as a series of gate operations, or in this case, a sequence of laser pulses. Blueprint, that's the idea. How do we do that? This is how the system really looks like. And what you see right here is indeed a real image of a chain of 100 ions. Now that's what we achieved after many years of development. Now these ions are really stock still in the ground state. They are there. And they can be individually addressed, and of course they are laser cooled by these lasers right here, and individually addressed by laser beams pointing to these lasers, to these ions. What ion do we have? As I said before, calcium is a 3-level system in the ground state, meaning there's a ground state S1/2 and an excited state D5/2. And we use only one of the Zeeman states right here. Lifetime is about 1 second. And there's a state right here that's connected with a dipole transition to the P1/2 state. So in other words, when you apply radiation at 397 nanometers and the system is in the ground state, then it should be bright. But once the system is in the excited state, or Hans Demel would actually say it's shelved on that shelf up here, then of course the electron is no longer available to shuttle back and forth, so it cannot scatter light. So indicating that there's darkness, but there's a projection going on because you have measured. So this is the system in the excited state. And this led in the 80s to the proverbial observation of quantum jump. This is a proverbial observation that we do all the time, always underlying, and gives us 99.99 whatever % detection fidelity, depending on how long is your patient to collect your light and to apply the radiation. Now, let's summarize these things. What we have so far is we have a 2-level system. I've prepared that, and that system is in the harmonic trap. So I have to rewrite my Hamiltonian in such a way that I have many of these 2-level systems which are just different by the trap frequency. And that, of course, is noted here by the quantum number n of the harmonic oscillator. So we just have a ladder system of n and the ground state and n in the excited state. And now I can tune the lasers to various conditions. Like in a vibrating molecule, I have a carrier transition that doesn't change the number n. Then I have a sideband transition to n-1. And that would just eat up one phonon. But the system in this case can be shown to decay predominantly on this transition. So finally, it would be optically pumped down to the ground state. And note, this is precisely the Sirac-Sola idea. Once we are there, we have prepared the quantum state according to Sirac-Sola. Once you're left there, you're only left with 3 transitions. That's the carrier transition, the so-called blue sideband, and the red sideband, because the system is so cold that higher order sidebands are heavily suppressed. They're not there. So in other words, we have the carrier to manipulate the internal superpositions, that's the qubit itself, and the sidebands to manipulate the motion and the qubit, or we create the entanglement that's intermediate when we just make all the operations. And if you want to know more, I refer you to these papers right here in more detail. Now we're ready. How does a superposition really, how does a calculation actually work with these superpositions? Now, as said before, we have this circuit, which is a sequence of 2 qubit and 1 qubit gate operations, and we have to make measurements. And of course, these laser impulses that we're actually using here are realized by carrier and sideband transitions. And this is tantamount to saying we're doing Bloch vector rotations in an atomic language. And the analysis can happen now by just measuring where are these populations in the register. But in order to figure out whether there's entanglement in the system, we not only can make a single measurement by seeing, okay, this is pointing up, this is pointing down, whatever, because that projects the system. We also need to rotate the individual Bloch spheres prior to making a measurement. This is what we call a state tomography, and we can even make process tomography procedures and get fingerprints. That would be the density matrix for the spell state. So all these 4 fingers pointing up here, the imaginary part should be really 0. And there's also some spectroscopic way to figure out that there's some entanglement. But let's assume that's what we do for a typical measurement. The real operations that we do are much more manifold. So in a real system, we have now the following toolbox. We have, of course, in a register like that, a beam that is globally applied to all of them, so we can make a resonant manipulation of all things simultaneously. Here are the typical time scales for laser pulses and the fidelities, and this would be the at-rest pulses. We do this only in an off-resonant manner because that gives us less crosstalk to the neighboring ions. So this is what we usually do, and the fidelities are likewise high. For the entangling operation, we could use the Sirac-Sola idea. But the Sirac-Sola idea heavily relies on the fact that we are always starting in the ground state. Suppose there's a slight possibility, a probability for having the system with an n equal 1 phonon in the system, a residual phonon there. Then the system would just not make a full rotation anymore because the Rabe frequency increases with the square root of number of the phonons, and then the system would be left in limbo. For this reason, we adopted some time ago for the entangling operation the so-called Mellmer-Skjørensen scheme, and this is something where we make use of two photon transitions. So we apply the red and the blue sideband simultaneously. When we do that, you see that starting, say, from both ions in the ground state, there's 4 pathways which lead to the same state, DD, in the excited state. Either you absorb the red first, then the blue, and so vice versa in the other states. And when you just add up all these probability traces, the functions, then you see that by quantum interference, the intermediate states just drop out. It's like any 2-photon transition in good old 2-photon spectroscopy. When you apply the laser counter-propagating, you can be Doppler-free. So motion doesn't really play a role. This is what we apply here, and that leads us to a very good, highly insensitive gate operation, where we can just do the entangling operations with these days with 99.9% fidelity. And it was shown a long time ago that these 3 blocks combined realize the universal gate set for arbitrary quantum computations. Now, for those who are mathematically more inclined, here are the unitaries. I'm not going to refer to all the unitaries, just to let them know how they look like. This would be a Stark shift, so it's the sigma C operation right here. And I will refer to these circuits later on only by the color-coded boxes on the qubit notation. So you just have the single qubit operations of the Stark shifts. You have collective Stark shifts, where you apply the beam collectively in a detuned way, or you have, say, the collective local operations, so you just make rotations about the x or y axis or any combination thereof. And finally, you have the collective operations with the 2 beams applied simultaneously. That's a sigma phi operation. So this is a dipole-dipole interaction that you have here. Essentially, that's the entangling operation. I'm not going through the mathematics here. It doesn't really matter. If you want, we can do that later. That's the details. In the meantime, we have developed over the last, say, 15 years, 20 years, many more operations. We can hide one of these individual lines by using non-participating states in the atom, so we can reduce or enlarge a computational subspace at will. We have dephasing operations, open system simulations. We can initialize or reset the system, and we have even a quantum cache memory. We can use 2 of these states in superposition to hide full quantum information while we do other operations on the system. That doesn't last long enough to do that forever, but long enough to do other operations in between. And then we can optimize these operations quite a bit. Then the next point is, of course, current quantum optics experiments. You have seen that here, and we have seen many of them probably before, look like that. That's not what we want. What we did is, over the last years, especially under the support of the flagship, the European flagship, we developed a prototype which, with everything in 2 of these 19-inch racks. So this is the laser rack, and this is the trap rack, and this is the inside of that trap rack right here. And if you want to know more, I refer you to that paper. And just to give you a few specifications of the system as it is right now. What we have right now is the following. We can actually do even more operations. So we have in parallel these 2 operations right here. We can make single qubit, 2 qubit operations as indicated here in a 2-ion at rest way out of a system up to 100 these days, not just 50. And this is the paper that I refer to. Specifications are as following. The T1 time is approximately 1 second, T2 time half a second. We routinely work with between 20 and 50 ions, and the newest experiments work with about 100 ions. We demonstrated 24 qubit the GHZ state up to 30. That's what we can do these days. We support all kinds of languages, Qiskit, Circ, or whatever you have. We have cross compilers. And the system can be automatically tuned up. So you boot up the machine. So within 30 seconds, the system just runs up and runs with 99% fidelity. If you need a bit more, you need a postdoc to tweak it a bit, but this can be done, and we are currently working on improving the system. So that's the workhorse that we have now in Innsbruck. Now it comes to some examples. What do we do with it? I've listed this under the heading quantum computation and quantum simulation. And essentially what this is about, you really want to use this machine for something that's hard to calculate on a classical computer. So you go to what I call a quantum simulator. Could be an optical lattice, could be an nine-trap quantum computer, superconducting, whatever you have. There's essentially three ways of doing it. The first thing would be a so-called analog quantum simulation. Analog really meaning we are replacing the system by, say, an interaction that you apply for a certain amount of time. So you just have a Hamiltonian that you really want to study. You apply via the interaction, say, an engineerable unitary in such a way that you apply it for a certain amount of time, and then you measure simply how the system behaves. Here you cannot do any error correction because the system really runs for a certain amount of time. You measure and you see how this behaves. On the other hand, a digital simulation is rather what we want to use for a computation, is exactly the way that I described it before. So you break down the processes in a sequence of unitaries that really replace the entire gate operation set, the entire computation in a gate operation set. And that's what is then finally a real computation, but it requires eventually error correction to get a sustainable result. This is not doable in the analog fashion, and quantum error correction is not completely solved at this time. I mean, it's solved in principle, but not in practice, meaning that we are not there yet. So you have to distinguish these, and that's why both methods still are valid approaches. There's a third approach that we call a hybrid simulation, where you use your classical computer to hold the problem, which is difficult enough so that it's too difficult to carry out the calculation in the Hilbert space of a quantum computer. So what you rather do is you simply say, okay, I have my Hamiltonian. I've come up with a series of, say, parameters. I address this system in a Hilbert space that I do, for example, in a simulator, right there, and I measure here just an expectation value, feed that back, and see whether this matches my expectations, my classical expectations. If it does, I'm done. If it does not, I let the system go and iteratively then determine what the outcome is. And this is also valid for some calculations, as I'll show you. So let me just start with the digital computation. The digital approach, as I said before, relies on the fact that you break down everything in a sequence of unitaries. This can be done with the so-called Trotter-Suzuki approximation. If you had a Hamiltonian and you write it here, then of course that Hamiltonian consists of parts that do not necessarily commute with each other. You can either apply the Hausbock-Baker-Campbell theorem and then you're done, or if you cannot because it's too complicated, then you resort to this. So you just replace this by piecewise application of the piecewise Hamiltonians right here for a certain time slice, put them together, that's what we call a full Trotter step, and repeat this n times, and then this approximates the unitary behavior, the finer the slices here are. So that's the digital approach. You can see more here. The analog approach, on the other hand, requires, as I said before, an engineerable interaction. So we really need to make sure that you have the interactions available that allow you to apply exactly the dynamical behavior that's then finally mimicking the dynamics of that Hamiltonian. So for example, let's take at this time this chain in this case, and we apply the bichromatic light from the side. Then you remember from the toolbox operation, this is the spin-spin interaction. And of course, the interaction strength can be tailored of the trap parameters and mode frequencies and things like that. But you always also apply these interactions in a non-resonant fashion. And that non-resonant fashion is described by sigma c operation. Combine this, you immediately see this is nothing but our good old-fashioned Ising model describing spin dynamics. So in other words, if you just apply the laser in said way, you really apply that engineered interaction and you can study the dynamical behavior in certain times. That can be done. So these are the two ways to do that. Just to give you ideas, this would be digital simulation, where we have broken things down in the trotterized version. This is a very early demonstration that we did. And you see here, this follows nicely the behavior for a 4-spin system. But you see there's a deviation between the open squares and the closed squares right here. The closed squares are the experimental results, that are the theoretical results. And the reason for that is simply that at that time, fidelities were not good enough. They are still not good enough to go much further. But you see, we run out of steam because you're accumulating errors because of repeated gate operations that you need to be undone. With error correction in place, you could do that, and that's the holy grail. But here we could not, and this is why analog simulations still have some attraction. Here's another more digital simulation where we did this to calculate 1D lattice gauge theory. It's just essentially the Schwinger model, or the QED in short. You see the Hamiltonian is written here for those who know that in a somewhat strange way. So from the Lagrangian, we write it down in terms of the Pauli matrices, because the writing this in Pauli matrices allows us immediately to apply the toolbox operations as I've shown you before. So we can translate that and immediately say, I know that term, applying this in the right order gives me the right Hamiltonian. And then you can see this is the trotterized version. You apply this program 4 or 5 times, and it's more like 220 gate operations about 10 years ago, then it was 8 years ago since we did this. And you see you can actually study the creation of a particle-antiparticle pair right here in the provided basis. These things can be studied. And in an analog fashion, you study phase transitions. There's nice papers by Chris Monroe. We have done that in a similar way with the spin model right here with the Ising model. He did it at low fields and then got some phase transitions right here. We did this at higher fields, meaning that we have we can rewrite this as a XY Hamiltonian. We see transport problems right here. A single spin excitation gets transported under the interaction that we have here. We create entanglement and can study that with long range and short range interactions. There's a ton of things doable. I don't want to go through all the details, give you just a flavor of what can be done. So for example, when we have the XY Hamiltonian right here, and add some disorder by just addressed beams, disordered beams applying in an addressed way these individual ions, we can just address different Stark shifts. That would be a disorder that we create right here. Then we see from a ballistic transport that we see right here, as indicated here, right there, we all of a sudden do not transport ballistically anymore. That's what we call an Anderson localization. Or if we just add a little noise to that one, then we get a diffusive enhanced transport. And if the noise gets exceedingly hard, then of course the noise says, no, come on, my qubit is being measured before I even can get there. And this is what we then say is a Zeno effect, essentially. And then you can study also hydrodynamic behavior. There's tons of investigations that have been done and will not be done with such simulators. Let me come and conclude here with the final hybrid simulation. The hybrid simulation, as I said before, uses a classical computer that holds the problem in a mathematical fashion, taps into a Hilbert space with a number of parameters, and feeds the system back, and finally you have to determine here whether you get agreement. That can be done again with the Schwinger model. This time, we are not interested in the dynamical behavior. Here we are interested in the steady state behavior. So for example, you want to figure out what is the steady state or what's the ground state of the Schwinger problem. And you see here it's done in such a fashion that we gradually approach the ground state. This is the error bar that we get in the end. Now you may ask, what are all these points here? I call this the Fleischert plot because there's dots everywhere. Why? Now the reason for that simply is that this machine has to tap into the Hilbert space with between 10 and 20 parameters. And eventually you have to make sure that you're not getting stuck in a local minimum. So you want to add a stochastic procedure to make sure that you're always getting out of the system until you're finally down there. Now, the question then is, how do I know when to stop? That's a tricky question because you usually exhaust your number of trials. So you come close to the ground state, that's what we see here. Or, and this is the good point of this, aside from programming the expectation value, you can also say my computer should actually calculate the variance. And if I calculate the variance, and the variance gets smaller and smaller and smaller, it goes to 0, then I know, I have found an eigenstate. So this is sort of a very self-verifying process that can be used in doing that. The underlying procedures can be used now to do molecular calculation, quantum chemistry. This has been done in our group. We have investigated the H2 molecule with some chemical precision, and we can do that for water. And these things are now being improved in various things. This is all toys. It's toy models. The chemists would actually laugh. The chemists here probably will laugh about this. I'm sorry, you're not good enough yet. But this shows how these things will eventually work once you have all the procedures in place, once you have enough qubits, once you have enough operations, once you have enough of these things. Which brings me to the point, when we really want to scale this up, the last point of this talk, and I hope I can stay in time. What is necessary? In order to really go to a full-scale quantum computer, we need, of course, more qubits in 1D, 2D, or even 3D. We need better control, we need more operations in order to do some quantum error correction. We need the computational power. This is actually software that's necessary. We need to know what is actually a key problem to be solved. The original problem was we can factor a big number, and people are still selling this to a certain extent. That's not the point anymore, because there's now other so-called quantum or post-quantum procedures, quantum hard procedures that are used for cryptography. But there are still problems around that are very hard. So chemistry problems will require too many qubits to do this. So that's why we are actually looking also for a key problem. For the theorists, think about it. I'm running out of time here. Let me just go ahead. What I personally think as an implementer of quantum computers, predictability is a very important problem. So when you go and to say, okay, I want to use, say, my IBM quantum computer or any other quantum computer of any provider in the world, or the AQD quantum computer, for an algorithm, can I actually estimate what will be the error eventually from the component performance? If I know that's the fidelity and that's the fidelity of the gate operation, what will be the outcome? Typically, you cannot, because this very much depends on the machine, the so-called error model, and this is not an easy task, in spite of what some vendors actually would tell you. Scaling down requires, of course, miniaturizing control hardware. We need definitely to scale down the errors with passive protection schemes or correction schemes, quantum error correction. We need faster gate operations, and we need scaling out. That's something that's usually overlooked. When we have one quantum device here and the next one there, can we parallelize that? Can I just make the entanglement across these distances? And can I really do the quantum parallel computing, the distributivity? And that needs an modular design, optical interfaces, hardware, but also quantum parallel processing software. Let me briefly go to some hardware devices right here. This is an idea that was issued by Dave Weinert some time ago to use these chips instead of these original traps. So you just have segments where you have operation, where you have interactions, where you have memories and things like this. And this requires chip traps, microstructured traps. These things have been essentially developed in many of these groups over the last decades, the last, say, 15 years, essentially. We have done our own, and this is available, all of these. And this is some of the ideas that were put forward by Ike Chuang from MIT. You could possibly then move all these ions in various segments, made the operations, and this can be parallelized. So you can actually say this would be a full-blown quantum error correction, just like Star Wars on a chip. You just put laser beams everywhere, transport these things very fast. And that's actually being pursued, for instance, by Quantinuum, another competitor in the United States. And but in the end, whatever you do, it comes down to making quantum error correction. I don't want to go through all the details. I just want to give you a flavor of what's necessary and what we can do and what currently the state of the art is. This is done in our laboratory with the so-called color code. It looks awful. So you have to create redundancy. Essentially, one quantum bit, a so-called logical quantum bit, is encoded in 7 quantum bits. You need redundancy to encode enough information to know where your errors are and finally how to correct them. Let's forget about this. These are all details. It's a black box eventually, so we have the algorithm. So you figure out what the syndrome eventually is. We call this a logical qubit. And this is just for bookkeeping. That's why we call it color code. You have to go around these things. You have to make the appropriate operations. These are just quantum operations. And you measure so-called stabilizers. And when they are +1, everything's okay. When they are -1, you figure out from bookkeeping which one goes wrong, and then you can correct for it. That's essentially the idea. that calls for a specific architecture making these things. So for example, suppose you had your 7 qubits arranged in a row, as we usually do. Then of course you have to write down where the error appeared. That's what we call an ancilla. But this is not good enough, because it may well be that errors propagate and that you have to take care of them. For this reason, we take an additional so-called flag qubit right here, where we say, if some error happened here, we are going to discard the system, because we cannot really make anything with that. So this is what the architecture says simply, and then we have the idea, let's make one logical qubit in, say, these 10 ions, and another one in these 10 ions, and then we get an array, a 2D array. In principle, we have already shown in that paper here in 2014 that we can make with these 7 qubits complex gate operations. This would be the X gate, the H gate, the Hadamard gate, or Y gates, by just making them what we call in transversal way. So we can make transversality really means a gate operation that you apply between logical qubits can be broken down in a parallel operation between adjacent physical qubits. For an implementer, this is all that you need, because that makes your life easy. And that's why we adopted that code. This calls for a technology like this. So we are actually producing at this time chips like that with the company Infineon. This is one of the chips where we have only 2 of these lines side by side. And right now they are manufacturing them with many sides. And we call this a quantum spring array. We do not want to move these particles like indicated in the MIT picture all the time. We just want to move them tiny bit, because moving them and controlling that takes a ton of time and is error prone, and that's why we don't try to do this. So this is our architecture, and we are really working on this very hard to get there. I'm essentially done with this. I don't want to bore you with this. The next step to do is, and there's much that has appeared over the last 3 to 5 years, is fault tolerance. Fault tolerance simply requires that you can control any error propagation. So once you have an error that appears here, you have to make sure that there are not 2 errors appearing, because you can control with your quantum error correction only 1 error. Once you have 2 errors, you're doomed. So you have to make sure I have a flag that tells me, no, there's 2 errors, just throw away the result. That's what we have done with this flag technology. There's many more papers, I can point them out, details don't matter. And the next thing then is you can make gate operations between 2 gates, between 2 logical qubits. That is yet to be improved. We have nowadays gate operations with about 80–85%. Now, that was the original paper in 2022, and this gets better all the time. And the next thing is that's required to make really universal operations in a transversal way. You need the so-called T-gate. T-gate is never transversal in the code that we have right now. Either you have to go to a different code, more ions, or you have to inject it. And this can be done in the same way. I know I'm boring you now, but I'm showing off because I'm telling you we can do that. There's no roadblock in sight. We can do these things, and we have already achieved, say, 99.4% here fidelity in creating these magic states. And you see that's quite an algorithm that's required, and a lot of things can go wrong. But all of these things, each block here is a C0 gate operation, so it's quite a bit of operations that you have here. Let me not go on further. Let me just summarize. What we are working on right now is, of course, on the logical qubits, quantum error correction protocols, fault tolerance, and we can correct for qubit loss. Another story. That is what I keep the qubit alive for the duration of the computation. That's imperative. The next thing that we do is, of course, for scalability, we need to get to bigger devices. That's what I called the quantum spring array, and we use then these traps also for quantum networking to interface them. And there's other developments. We can enlarge the Hilbert space for the computation by using more states than just one. So instead of qubits with b equal 2, we just use qdits, where the d can go up to as many states as your system provides. And that is, I think, a very helpful technology, but I won't have the time to go into that. Let me give you my dream. My dream is, of course, and that's the vision, to come up with a structure like that, where we have groups of these ions which are interacting as logical qubits and are error corrected and are continuously driven such that we can operate the system for a long time. But then there's all these fancy newspaper articles like in Time magazine and others. You see that was already an article in 2014 and similar in 2023. There is the fiction here. will replace classical computers, are better than classical computers, or always faster than classical computers. There's a big question mark that I want to make here. So let's just discard this for a time being, and let's see what the facts are. The facts are, of course, that we have quantum computers as universal computers. We use superpositions and entanglement. We have quantum information which is more volatile than classical information, but quantum error correction works. We have shown that, and we are about to implement this. They are faster than classical computers, but not for everything. If you want to add +1+1, don't do this on a quantum computer. This works better on a classical one. And quantum computers are already reality to a certain extent. But fact is also, when we just look at these green marks, that currently we have, say, 100 qubits available, say a few hundred with IBM and others. And the 500 to 1,000 gate operations, maybe a few thousand. But competitive applications where you really want to go need on the order of 1 million qubits and of order of 1 billion and more gate operations. It's a long way to go. So currently we are studying so-called NISQ, noisy intermediate scale quantum computers, to do where we go. And then, of course, the holy grail is to fulfill all these things that you see always as the carrots in front of you. Yes, this green mark, secure communication, that'd be something we can do these days with very few qubits and quantum repeaters. We do actually do financial market analysis for some companies. I don't know on the why and how this works, but companies tell me that they work on our computers that this is already doable. Material science, high temperature superconductor is a dream, and all that, the further you go to the right, the more difficult it gets, and there's a long way to go. So let me just sum this up. There's plenty to do. There's nice stuff that we have been doing. We've been lucky to live in such a time to see all this nice stuff being done. But what we really need is still to keep the qubit alive, at least for the duration of the computation. And this is, of course, a large group that did the work. It's not by me, and supported by very, very many theorists. Otherwise, it would not have worked. There's, of course, the names, but let me just show you where we are. This is Innsbruck from the top of one of the mountains, and this is close to the airport where the quantum computer lives. That's the home of the quantum computer. And this is how it really looks like now with AQT, if you can buy that one. With a 50-qubit system, upgradable, modular design, and fully programmable. We have deployed already 3 of these systems in Europe alone, and we are selling also traps worldwide. So if you want to buy one, contact Thomas Mons. And essentially, that's the CPU, or now QPU, that we have. Thank you very much for your attention. Sorry, that was overtime.
Yes, thank you so much. That was a truly remarkable overview of where trapped ion quantum computing stands today. And I think it gave a lot of us to think about, because the progress is huge. So now we have a time for questions, please. The floor is open. Okay, Domantas Burba.
So thank you for a nice talk. So on one of the slides you flashed this like spin-spin interaction that they interact by this power law with like tunable exponent. But how exactly do you tune this exponent? Do you control distances between these ions, or how do you do this?
We can control not the distance between the ions, but the interaction between the ions. This can be done by the respective detuning and the Rabi frequencies that you apply. We can talk offline about this. Okay. There's various papers that have theoretically calculated that. And we cannot do this at will. Let's just give you an idea. When you just have 2 naked charges sitting right next to each other, that's a Coulomb-Coulomb interaction. Okay, then you would say that's, of course, not only nearest neighbor, because that Coulomb interaction talks to the next one as well, but less so than to this one. So then the interaction trails off. But now, since we have a phonon, when the phonon, of course, talks to all of these at the same time, then, of course, that interaction is as strong over there as it is here. So you can actually, by making the phonon and the kind of interaction that you have there, then you can tune the system between, say, all-to-all, up to double interaction close. That's that exponent between 0 and 3. Effectively, we can do this between 0.5 and 2.5, not better.
Okay, any more questions from the audience? Yeah, this pabrėža.
Thank you for the very interesting talk. My question is about lasers. So you use 2 lasers. One is blue, the other is red. So is it slightly off-shifted from the main absorption line, or how?
We use many more lasers. In fact, in order to operate the system, As this, we use 5 lasers. So, but okay, so we use the 2 lasers for cooling and preparation. That's a laser at 397 nanometers. That's simply for optical pumping and excitation for we measure. And for repumping is used the laser at 854 nanometers. So these are the 2 basic lasers, and they are switched on to prepare the system. But then the qubit laser is a laser at 729. And when we want to make the gate operation, of course, works by these 2 photon transitions, so one red sideband and one blue sideband simultaneously. Now, in order to make that can be done resonantly, but that's not very good. So you have to get a slight detuning, because you also have to make sure that you compensate for existing Stark shifts. That detuning from the center resonance frequency is only about 20 to 30 kilohertz. So it's not a big deal. That laser, on the other hand, needs to have a bandwidth on the order of 1 hertz.
1 hertz.
So yeah, you don't get something for free. There's nothing like a free lunch.
But is it one laser which is somehow split and offset, or is it
That's essentially one laser that's split and offset. The acousto-optic detectors, acousto-optic modulators. So this is, of course, I learned this from Jan Hall a long time ago. So for me, it's not a big difficulty. But I know some people, good, 1 hertz laser, it's not a big deal. Nowadays, people can do that.
And you mentioned it's a pulse laser, so is it
That's not a pulse
gated,
laser,
or?
that's a continuous wave laser, because we need the coherence time.
Yeah.
The pulses are just done, of course, by acousto-optic modulators. And there's pulse shaping involved, and you have to be very careful with
more like
that.
Gated with acousto-optics, right?
With acousto-optics,
Chopping.
chopping,
Yeah.
it's tailored chopping, precise chopping.
Okay, thank you.
So to avoid that you get off-resonant excitations.
Sure, thank you.
So there's a bit more involved. There's some dynamical decoupling. I'm not talking about the gory details here, but they are underlying.
It's always big picture. Any more questions? Okay, there's that. Aha, okay. Taip, Andrius Jotagalvis.
Thank you for interesting presentation. I was curious about the qubit system, probably overslept explanation, whether calcium ions are floating in the device. Can you lose a calcium item from the system and you have then a different system?
These calcium ions are living in an ion trap. That ion trap is relatively steep, meaning that the potential well depth is on the order of an electron volt or so. So, and of course, the excitation is the ground state. So typically, we don't lose these ions. We can just keep these ions for weeks, if you like. You lose ions only inadvertently when the laser just goes completely out of resonance, or if you have, say, a very bad collision, which usually doesn't happen. So when we lose ions usually that's ion loss, what we call that, or a qubit loss. We use that ion because it just gets lost in a wrong Zeeman state. And then we have to track where it is, and then we can repump it. So that's what we usually have as a loss. There's one loss mechanism that I did not mention, and nobody does it. Of course, you don't want to mention all the bad things. That happens when your vacuum is not good enough. It could very well be that this calcium forms a calcium hydride, or in rare occasions, calcium hydroxide. And this appears in a chain then as a dark spot, because that's a different element, it has a different mass, that's how we actually can see it. And we can throw that out, but that happens once in a while, say once every few hours.
So in principle, you can recreate the qubit system whenever you need it.
Oh yes, we can do that. It's not a big deal. But other people use also, say, a reservoir of atoms, and they move the atoms and ionize them. So we usually just gently do photoionization from a pulsed source, laser ablated, and we can just add one atom by atom.
Thank you.
Any more questions? Yes, you have now time to think. In your almost last slides, you talked about fault-tolerant gate demonstration. You talked about 2 qubits, logical qubits. Yes, you clearly demonstrated their logical error suppression below the physical error rate. So how comfortably below threshold is Innsbruck system today, and what is single biggest obstacle for getting farther?
So the question is, what's the threshold that we have at our system?
Mm-hmm.
That's a tricky question, because this is not simple to answer. We calculate from the error models that we have right now, and this is numerically done with partner groups. in Oxford and other words, we estimate that the error threshold is somewhere as 2 to minus 3, and let's say 1 times 10 to minus 3. So we have, with a gate fidelity of below 10 to minus 3, we should be in business. Yes. We do have that, but this is, sometimes it works, sometimes it does not. So we have to make this better. So at this time, there's research going on. What limits the current fidelities? That's the 2-qubit fidelities. And then, of course, how do they scale? And I have a bunch of ions that are not constant, not necessarily. So this is something we have to study. And for this reason, we also have studies going on with the different ion species. See, one of the problems is with the calcium, it has only a lifetime of 1 second. And so once the D state is involved, and you have a few 10 microsecond pulses, then already the system starts to decay, your Bloch vector starts to tip. That already leads to an error which has to be taken into account. That's not, can be done, but it's annoying. For this reason, barium is much better suited because it has a lifetime of some 40 seconds. Then also the wavelengths are different, and we have different ways of making gate operations. So in barium, you may win factors of, say, 20%, 30% here and there. So overall, we expect it to be a factor of 10 better. That's currently being done in the lab, and nobody knows more. That's at least where we go. Quantino, for example, is using all the time 2 ions. They are using barium plus ytterbium, where the ytterbium is used for a qubit, and the barium is used for cooling and for readout operations. So that's one way of overcoming these shortcomings. There's another way of doing this, doing gate operations right now by Raman transitions, which are far tuned, say with a laser at 532. That would add another laser, aside from the lasers that we already have. This is not finished business. People claim, for example, in Oxford, that they can do 2 gate fidelities of 10 to minus 6 even. So in principle, it's possible for 2 ions. Come on, what do I do with 2 ions? My logical qubit consists of at least 10, and in our case, we probably might need, for our error correction stuff, we need probably a color code with 17 ions plus 3 ancillas. So that would be 20 ions. So the array that I've shown you, 10 is not good enough. It would be 20 in one line and 20 in the next line. That is the current architectural way of thinking that we have. Whether that survives remains to be seen. This is active research. So, tricky question.
But thank you for the answer. Any more questions from the audience? Audience is still compiling. So you mentioned that trapped ion systems offer a high fidelity in comparison with another qubits. For which class of computation, let's say simulation, error-corrected algorithm, do you think trapped ions will demonstrate a clear, unambiguous quantum advantage first?
I wish I knew. Yes, thank you. No, but what we are pursuing is the following. Of course, quantum advantage is pursued by so many, and the good result would be if you could do, say, a chemistry calculation. But a good chemistry calculation that is clearly surpassing the possibilities, the abilities of a classical computer would require on the order of about 10 to the 5 qubits at the least, and a few million gate operations. That's far from what we can do. What I personally would like to see is physics problems. I'm a physicist, but first and foremost, so I would like to solve a problem that is closer to my heart. And the Schwinger model was a toy model that we saw, and in the meantime, we've done the Schwinger model with 2 dimensions. In 2 dimensions, I'm not going to talk about this here right now in detail, but when you just have a lattice gauge theory, then you implement also in a classical computer, your fermions on a lattice side, and the interactions between the fermions are necessarily encoded like bosons, because if they're occupied, then the field, depending if positrons or electrons right here, points in this direction or that direction, or there's nearest neighbor, then it's a bit more there, a bit more there. So essentially, that's at least a boson with a spin 1, so 3 states, this way, or 0. Or if you have more than nearest neighbor, then it could be 5 and more. That's how you do it in a classical computer as well when you do these calculations in QCD, like quantum chromodynamics. Quantum electrodynamics can be well studied in perturbation theory. What cannot be calculated to this time is quantum chromodynamics when you go for the strong interactions, especially when it comes to color charges, when it comes to larger systems, not even with, say, as many as 40 points in a lattice. That's very, very hard to do in physics. And here the question was, can we contribute to that? In a 2D lattice geometry, we have already shown we calculate the so-called Wilson plaquette. Wilson plaquette consists essentially of a periodic with periodic boundary conditions of, say, 4 sides. So you just close them on all sides, so they get a quasi-continuum. But the point simply is, in the Wilson plaquette, the currents can go all the way around. And currents going all the way around create a magnetic field, necessarily, which is not the case in a one-dimensional case. And that can be calculated, and we have simulated that. And the point is, right now, we are really working hard on this. This seems as if we can generalize this to 3 dimensions. And then we are in business, because then we have the first 3D operation for QCD. Next thing to do is non-abelian operations, and this is something we have done in a different experiment. We have to put it together, and finally we have to do the strong coupling constants. So that's the program I have for the next years. I'm not sure whether I will do this, but that's what I hope for. I want to have a calculation in physics that does more than you can do on your classical computer. Then I'm happy.
We are happy to hear this. Okay, Evaldas.
One more about lasers. So
sure.
You mentioned
lasers are important. I'm happy to see that lasers manufacturers here. So if you have good lasers, come to me, and we need all the lasers.
Yeah, we'll talk tomorrow in more details. But 1 Hertz laser, do you know maybe if that's achievable only with ring cavity lasers or also with ECDL?
We do that with ECDL.
ECDL diode lasers, yeah.
Yeah, it's just diode lasers and just power amplifiers.
Okay, thank you.
It's doable. I know how to do that.
Okay, people, last chance to ask the question. Or I will take that. Okay, scaling, yes. Superconducting qubit chips control lines are fabricated monolithically with the qubits. And you showed some paths. So is it realistic path toward integrating photonic or microwave delivery directly into ion trap chip?
Yes.
So, yes. So that free space
yes,
laser
it
beams.
is.
Yes.
It's realistic, and it's one of the projects that's already going on for the last 2 years, and of course will go on for the next years. So we are trying to produce. I didn't have the time to talk about the chip that you saw. Is a chip that is done in collaboration with Infineon Technologies. Infineon, the chip manufacturers in Austria, are very big. The chip factory in Villach. And the next step that we do is we already do that not with Infineon, but with other chip manufacturers. We are integrating together with ETH Zurich and others photonic waveguides on the chip to deliver the light onto the chip itself. The next thing, what Infineon can do, all the electronics that we need to steer the trap can be underneath the chip. So we don't want that to be outside because we need cables and everything else. And then, of course, the next thing to do would be to integrate also detectors on it. That was done already, pioneered by the team, by Dave Weinland's team, or former team by Dave Weinland, a few years ago in Boulder, Colorado. Whether we can actually integrate all of these in one chip, that remains to be seen. But this is work that is necessary. I mean, come on, in the end, where do you want to go? 100 qubits is not good enough. 1,000 is not good enough. We want to go to a few thousand, to a few 10,000, or if you want to go to 1 million. That does not work with cameras and lenses and optical tables like that. So we have to just pack everything in the chip.
So on this nice note.
There's room for improvement. There's room at the bottom. You're welcome to help us.
Yes, there is a room, and we wait for all of you. So let's give a big round of applause. Yeah, thank you so much. Thank you.
All weekend I was wondering what I can do in 10 minutes. So either you can make a coffee, have a cigarette, have a break, or I don't know, defend your bachelor thesis. I'm not sure how long now they let you to defend it. But I will try to give you a small presentation about company Expla and 2 of many applications that our lasers are being used in. So at first, who are we? So some of you may know, some not. So we are the developers of advanced lasers, as well as electronics for lasers, which are being used by other manufacturers of the lasers. We develop lasers for industry and science, spectroscopy imaging technologies, high-intensity lasers, laser systems. And one of the most important things, of XPLA is that we are one out of 4 or 5 companies all around the world which has won 2 PRISM awards. And if you don't know what this PRISM award is, like an Oscar in laser industry. So that's quite a huge accomplishment. And we work with many different institutes, universities, starting from NASA to LA Alps, to Oxford, Cambridge, Harvard universities. So now the topic was laser that drills and laser that listens. So I believe that laser that drills, you already figure out, like it's self-explanatory. You know that we can do many things with the laser, cutting, ablation, drilling, etc. But in this case, it's important because we are talking about drilling of a glass substrate. And you know that the glass is quite fragile, and just drilling with any mechanical equipment, etc., may shatter the glass. But having a laser with stable pulse-to-pulse energy, we can drill through the glass pretty in high-quality holes. So here you can see an example on the left how the high-quality drilling, or so to say, through glass via can be done. And on the right, you can see how it can be done without stable laser, let's say. This is important because nowadays, if you are interested in microchips, technologies, and electronics, you know, probably you have heard of Moore's law, which states that there is a limit of how small we can make the microchips. So in this case, a through glass via application can help us, let's go to this slide, can help us to sandwich different microchips into like one chip, so to say, which looks like this. And in this case, we have a microchip on the top. We have glass substrate as interlayer as a insulator. And in this case, we need to cut the holes through the glass, which will work as a contact to connect through several different microchips. So it's called advanced packaging. Another topic, since I have only 10 minutes, another topic is light that listens. So this is a bit more intriguing. And does any one of you have heard of the term photoacoustics? Some of you have heard. This is quite an interesting topic, and I will show you some of the results that our colleagues from UCL, University College of London, have achieved. So in this case, how it works is that we irradiate a human body, or let's say in this case, a hand with some inflammation on the skin. And this laser, in short, we irradiate the body with the laser, and we get photoacoustic waves from the body, which we register with ultrasound detectors. And in this case, you can see how we can analyze how the inflammation throughout the days goes away. But interesting topic is that they achieved very fast response. Their equipment, they are using our laser with their own equipment, and they achieved very high response from the fingertip. In this case, they cut off the bloodstream in the finger, and they released it, and you can see that the blood and blood vessels was detected just in a fraction of a second. So you can see here on the video. So this response is important because photoacoustics can be used, can replace ultrasound imaging. And with higher quality of image we can get from inside our body. Where everything started was Agata system. With our partners, we created a system focused on breast cancer research, or so to say, analyzing and detecting breast cancer cells in breast in early stages. So we created this system, and it will in the future replace MRI or not so comfortable for woman mammography equipment. This is much faster because the analysis can be done in 2-3 minutes, and it can be repeated the same day several times to definitely know if there are some cancerous cells or if there are no cancerous cells. And with this equipment, this specific equipment, we can get 2D. Here you can see 2D images. In short, how we can say that the breast has some tumor or cancerous cells inside the tissue is that cancer loves oxygen. And in this case, when there is a cancerous cell, there is capillary clusters forming around that cell to bring oxygen to that cell. So in this case, you can see an example of breast cancer. And the marked area is where the cancerous cell is located. For comparison, this is the healthy breast, and you can see that there is no capillary clusters in the tissue. Also, with this system, you can get 3D images. And of course, not only with the breast, it can be done with the brains, lungs, hands, legs, I mean, whatever you think of. So that's quite unique, and now it's the hot topic in medicine research, is applying photoacoustics for such kind of diagnosis. And that's it for me. I'm not sure if I took 10 minutes, but if you have any questions, you can ask. You can keep in touch. You can scan this QR code. You can contact us. So, any questions? Come on, some. Yes.
So how are you, in the photoacoustics experiments you showed, how are you generating acoustic waves with lasers?
In this case, we are using our laser, photosonic series laser, and we are using wavelength from 680 nanometers to 1100 nanometers, and we are scanning all the range. I believe you had like ultrasound imaging once in a lifetime. So we are scanning the body, and we are, through fibers, we are illuminating the tissue with a laser, and it's heating the molecules, which starts to vibrate and gives photoacoustic waves from the body. So we register those waves based on which wavelength we got those photoacoustic waves. So for example, arteries, like hemoglobin who carries oxygen absorbs one wavelength, and hemoglobin which does not carry oxygen absorbs other wavelength. One more, come on. Everyone's so serious, it's just a Monday, not Friday. Be more energetic. Another one. Yeah. Oh, no. I can show you. I believe maybe. So, yeah. So you see I'm not sure if I will be able to. Yeah. So here is like a bowl where you put a breast in, and this bowl has a couple hundreds of fibers which directs the laser beam into the tissue, and also we have ultrasound transducers which catches the photoacoustic waves and then registers in the system which translates those waves to 3D images. Did I answer? Yeah. Yep.
Do you have clinical approval for that, or is that like earlier stage?
Oh, this one, specifically this system is already after clinical trials. Clinical trials began 2 years ago, maybe a bit more than 2 years ago. So they are, the clinical trials are done, but you know, there are more bureaucracy to up.
I was wondering about.
Yeah, but it's this one is quite old, let's say, but yeah.
Okay, any more? No one?
One more. None? Yep, okay.
One more question. So for this blood which has oxygen and blood which doesn't have oxygen, would it be possible to just use two discrete wavelengths at 700?
There is a range of wavelengths in which the hemoglobin which carries the oxygen is absorbent, let's say. And then there is another range where hemoglobin without oxygen is absorbent. So it would be, but having that wide range, how to say, it helps to make it faster. And like, since the pulses are very short and we scan through the wide range, if not one pulse is absorbed, then another pulse is absorbed, let's say. So just shooting one wavelength would be enough, but it will take longer time to get the results.
Okay, thank you.
Okay, so if no more questions, let's thank the speaker.
Thank you.
Thank you.